Atoms are submicroscopic particles that are the basic building blocks of all matter. We can't divide atoms by chemical processes. Only nuclear processes can do that. However, we can take atoms, react them with one another to form different materials. Atoms are very, very small. They have typical diameters anywhere from about 70 to 400 picometers. This is way too small to see with the naked eye, or even optical microscopes. To put this into perspective, the average width of a single human hair is between 100 and 200 micrometers. Atoms are about 1,000,000 times smaller than the width of a human hair. Atoms come in different types, called elements. Different elements have different physical properties, chemical reactivity, and size. Some elements are gases in their native state, some are solids, some are liquids, some are like uranium, or even radioactive. Elements differ because they have differing numbers of protons in their nucleus. The number of protons in the atom's nucleus is called the atomic number. Wow, with all these different materials, how can we make sense of it all? How can we organize these different chemical elements? The periodic table of the elements does just that. It lists elements in order of increasing atomic number. Remember, that's the number of protons in the atom's nucleus. In addition to simply arranging the atoms in order of increasing atomic number, elements are arranged into vertical columns called groups. It's important to remember this because these elements within a certain group exhibit similar chemical reactivity, similar chemical behavior. So we can actually make additional sense of the periodic table based upon an element's placement in a particular group. This particular periodic table was published by the International Union of Pure and Applied Chemistry. It reflects 118 known elements known to man. Some of these elements decay very, very quickly and only exist for a fraction of a second, but nonetheless, they've been demonstrated experimentally. Another thing to know about this periodic table of the elements that's important to keep in mind, it's really a living, breathing document. It can change over time. As new elements are discovered, they can get boxes on the periodic table for themselves. In addition, the data can be updated or improved. For instance, it's not uncommon to see atomic masses change when more exact or precise measurements of the atomic mass are provided. If we study each box on the periodic table more closely, we can see that additional information can be gleaned. Take, for instance, the box labeled Fe in the middle of the periodic table. This is the box for iron. Fe is the elemental symbol for iron. Each box has its own letters, corresponding to its characteristic element. Sometimes the common name for the element is also included in the box on the periodic table. Some additional figures are reported in the periodic table boxes as well. First is always an integer. This is the one that's at the top of our box for iron. It's labeled 26. This is the atomic number. Again, this corresponds to the number of protons in the atom's nucleus. It's what makes iron iron. Atoms that have 26 protons are always iron. From this information, we don't know how many electrons that a particular atom of iron will have. If it's a neutral iron atom, it will also have 26 electrons. However, iron can also exist as ions with differing number of electrons. We'll get to that later. An additional number that's in this box is the atomic mass. For iron, this is 55.845. Each element will have a different atomic mass. This is an atomic mass units. It's more or less a weighted average of the mass of naturally occurring iron atoms in nature. It's important to realize that this atomic mass does not represent the mass of any one particular iron atom, but rather is a weighted average of the different isotopes that iron can exist as in nature. So no particular isotope of iron will have this one specific mass, but it's a weighted average. It also tells chemists the mass of 1 mole of iron atoms. This will become a very, very important concept in General Chemistry 1 because the mole is the base counting unit that chemists use to keep track of how much of a material they have. It's a pretty simple idea, but can sometimes be confusing. A mole is simply 6.02 times 10 to the 23rd atoms of an element or molecules of a compound. It's a counting unit, much like we count eggs in terms of number of dozens. Now we've talked about how we all know 1 dozen eggs is equal to 12 eggs. Likewise, 24 eggs is 2 dozen, 36 eggs is 3 dozen. It's almost common knowledge to be able to convert between the number of eggs we've got and the number of dozens of eggs because it's so familiar to us. Well, chemists also have a convenient counting unit. It's called the number of moles of atoms or molecules. Moles, M-O-L-E-S. You'll see this a lot in your chemistry class. It turns out that moles are analogous to like dozens. It's just that the number of atoms or molecules that make up a mole is very different than 12. In fact, it requires 6.023 times 10 to the power 23rd atoms or molecules to make 1 mole of particles. This concept can be applied to anything. If we have 6.023 times 10 to the power 23rd quantity of any item, we've got 1 mole of that item. Now, this number is much, much larger than 12. In fact, it's incomprehensibly huge. If we tried to count that by ones, we would never make it before we pass away. It's way too many to count. So we're never, ever going to count atoms or molecules up to figure out how many moles that we've got. Instead, we're going to use mass. In fact, this number is so large that if you were to take oxygen atoms and line them up side by side, and you lined up 1 mole of these oxygen atoms, the distance would exceed the Earth to Sun distance. So this number is huge. Well, if chemists cannot count how many atoms or molecules are present in a sample, how do we know how many moles are present? The answer is pretty simple. We use something that we can measure, that's experimentally observable. That's going to be the mass in most cases. We can easily go into the laboratory and measure the mass of a material that's present and relate that to the number of moles of that substance that's present. It's important that the substance is pure for this to work. Let's take the case of the element Mo. This is molybdenum, element number 42 on the periodic table, meaning that all atoms of molybdenum have 42 protons in their nucleus. If we look at the box for the periodic table for molybdenum, we also notice that there's this number 95.96 in the bottom. This is the atomic weight. This corresponds to the number of grams in 1 mole of molybdenum. If we go into the lab and measure out exactly 95.96 grams of molybdenum, we would have 1 mole of that element. If we measure other masses, we could have more or less than 1 mole of molybdenum. Say, for instance, we go into lab and we measure out exactly 94.56 grams of this element, as shown in the picture on the left. This is approximately 1 mole, but not equivalent to 1 mole. In fact, it's a little less than 1 mole because we know it requires 95.96 grams of the element to have 1 mole. We've got about a gram less than that or so. But we can figure out how many moles we've got by simple division. We take the mass that's observed, 94.56 grams of sample, and we're going to divide that by the atomic mass, 95.96 grams. Again, this is the quantity or the mass required for 1 mole of the element. If we do the simple division, we find that the result is equal to 0.09854 moles of molybdenum. And sure enough, that's how many moles of the element is present in the sample that was massed out in this experiment. Alright, so we've heard a good bit about atoms, or elements from the periodic table of the elements. You may have heard of molecules and be curious about what they're all about. Let's take a few minutes to expand upon that idea. A molecule is simply a substance that is formed when atoms from the periodic table combine in specific whole number ratios. In this particular example, we'll consider the water molecule, very common substance. For every water molecule consists of 2 atoms of hydrogen that are covalently bound to 1 atom of oxygen. Hydrogen and oxygen always combine in a 2-to-1 ratio to make one water molecule, H2O. Chemists use the subscript 2 to denote how many copies of a particular atom are present in a singular or one water molecule. The bonds that hold atoms together come in various different lengths and strengths. Some bonds are very strong, others are very, very weak. Some involve sharing of electrons, and in other bonds, the electrons can be transferred between the partner atoms. But the important thing to remember about these bonds is that they're forces that hold the atoms together to form a molecule. They're required to form our molecules, okay? A molecular substance, then, that results from a specific whole number combination of atoms is its own unique molecular substance. It has its own unique properties, both physical and chemical, and while it can undergo chemical reactions to rearrange the bonds, break some of them, maybe make new bonds, that molecule itself is a pure substance that's unique. So water, for instance, boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. It reacts violently with sodium metal. And by application of a voltage, we can actually break water molecules apart back into its constituent elements, hydrogen and oxygen, in a process known as electrolysis. So molecular substances have their own unique physical and chemical properties. Now, in the previous slide, we learned all about how we could combine atoms from the periodic table of the elements together to form different molecules. And each molecule, with its own unique substance, it has its own physical and chemical properties. We're going to learn about another property of chemical reactions now in this slide. And this is the law of conservation of mass. It turns out that in any chemical reaction, when molecules react, mass is said to be conserved. And we can see this in this simple example. Let's consider making a water molecule, H2O. We said on the previous slide that our recipe for making 1 mole of water is combining 1 mole of oxygen atoms with 2 moles of hydrogen atoms. So we can make Avogadro's number of water molecules, that is 6.023 times 10 to the 23rd molecules of water, using these ingredients. We need a mole of oxygen atoms, and we need 2 moles of hydrogen atoms. And this is because of that fixed whole number ratios with which these elements combine to form water. Now, interestingly, if we were to mass out 1 mole of water, or record the mass of 1 mole of water, want to know how much that weighs? We can easily find out how much it weighs by simply combining the parts, combining our ingredient list. And this works because mass is conserved in all chemical reactions. So to demonstrate, let's think about how to compute the molar mass of water. To do this, we would combine 2 moles of hydrogen atoms, each having a mass of 1.01 grams per mole. That latter number, 1.01, is the mass from the periodic table. We're going to add that to 1 mole of oxygen's mass. This is 16 grams per mole from the periodic table. We sum it up or add it, we find that a mole of water should equal 18.02 grams per mole. So 1 mole of water has a molar mass of 18.02 grams per mole. This is referred to as the molar mass of water. And for any molecular substance, you can arrive at the molar mass by a similar calculation. You simply have to add up the component parts from the periodic table that build that molecule. It's that simple. So say, for instance, for methane. Methane is a molecular formula CH4. It's got 1 carbon atom in the center, which is bonded to 4 hydrogens, here shown by the white spheres. The black sphere in the center is the carbon. CH4 is, again, its formula. If I want to find the molar mass for methane, it's simple. We just add the parts. We've got 4 moles of hydrogen atoms to make 1 mole of methane. This means we have to multiply 4 times the molar mass, 1.01 gram per mole, from the periodic table for hydrogen. This is 4.04 grams per mole. And I'm going to add that to 1 mole of carbon atoms, 12.01 grams per mole from the periodic table. So I combine 12.01 grams per mole, that's the carbon contribution, plus 4.04 grams per mole, that's my hydrogen contribution, and sure enough, 16.05 grams per mole is the molar mass of methane. So 1 mole of methane has a mass of 16.05 grams. It's that simple.